Hello everyone. The topic of our final year project is optimal capacitor bank placement and radial distribution network using PSO and genetic algorithm. My name is Engineer Arif Ali Kokar and my group mate is Engineer Abdul Muin Sheikh. An electric power system is a network of electrical components deployed to supply, transfer, and use electric power. When electric power systems are expanded and become more interconnected, the losses in distribution network will increase, which cause decrease in power factor and voltage profile level. Optimal size and location of shunt capacitor in the distribution system plays a significant role in minimizing the energy loss and the cost of reactive power compensation. In addition to this, we will also ensure the types, cost, size, and optimal location for placement of capacitor banks. Basically, the motivation behind making of our project is an existing radial distribution power system. Capacitor banks are placed on almost every substation, which is not economically efficient. Due to this, the system becomes more complex. So in order to overcome these problems, our motivation is to design such system which is cost efficient and less complex by placing capacitor banks only on the buses where losses could be reduced and voltages can be enhanced in the power system. So the problem statement behind our project is about 13% of total power generated is consumed by power losses at the distribution system. However, due to this, the system has low voltages at far end buses and distribution network, and high power losses in radial distribution system occurs. Also, high reactive power flow in radial distribution network as well as low power factor due to the high reactive power flow in the electrical power system. So in order to understand the complete idea behind our project, we have done some literature review. Our first author said, Hussain Lutfi and Mohammad Samadi said, the title of their paper is Optimal Capacitor Placement and Sizing in Radial Distribution System using an improved particle swarm algorithm. This author proposes particle swarm optimization, PSO, and other revolutionary capacitor placement strategies in radial distribution system. The genetic algorithm and the particle swarm algorithm are combined in this strategy and are used to determine the position and appropriate size of capacitors. Moreover, the other author, Qasim Kumail Masan, said, most of loads in distribution networks are inductive due to the nature of system. For example, transformers and power lines, while most devices used in the homes or most motors that are inductive in nature, which consumes reactive power. For these and other reasons, voltage profile will be reduced and energy losses will decrease. Professor Hashim Abdul Rahman said, their title of paper is Allocation of Distribution Generation in Capacitor Banks in Distribution System. Basically, particle swarm optimization is used in this research to efficiently solve the problem of simultaneous capacitor banks. Moving forward, the aims and objective of our project is to achieve the minimum of power losses, to ensure the voltage profile within constraint, and to find the optimal position of capacitors to be installed in radial distribution network using PSO and genetic algorithm. Throughout our project, we have used the methodology, which is we have designed and analyzed IEEE 33 bus system and 69 bus system in PSSE and MATLAB software. Also, in each system, a comparison is made among nominal system with capacitor banks in the radial distribution system. We have also injected capacitor banks in systems, and 3 different techniques for analyzing our system has been utilized. These 3 techniques are Tendral method, PSO algorithm, and genetic algorithm. The results and discussion we have discussed, we have used 3 techniques. These are 3 methods used in our work through which we will obtain the results. These 3 methods are, as I already discussed, number 1 is Tendral method, number 2 is particle swarm optimization, PSO method, and number 3 is genetic algorithm method. Basically, we have designed IEEE 33 bus system in power system simulator for engineers PSSE software, in which this is an idea of 33 bus system. You can see that bus 1 is a select bus, while other buses are load buses. in which different ratings of loads are connected, which causes low profile of voltages, low power factor, and high power losses in the system. Basically, we have taken results using our first technique, which is hit and trial method. We have optimized the system through hit and trial method. You can see figure 1, where nominal losses of the system are 180 kilowatt losses, active power losses. We have placed capacitor rating of 800 kVAr on 3, 13, and 14 bus. By this, we have achieved the losses till 170 kilowatt losses. Also, we have placed different rating of capacitor like 500 kVAr rating, which gives losses to 160 kilowatt losses. Moreover, you can also see that we have changed the number of buses, the location of buses, and as well as capacitor rating in order to give the overall, in order to understand the overall idea of the system, how system behaves when we place the capacitor banks in the system. Like the nominal system losses are 180, and we have achieved till 140 losses. However, these are not the optimized results. You can see at figure 4, these are the optimized results. We have placed capacitor on 17, 26, and 29 buses of rating 700 kVAr, through which we have achieved 130 kilowatt losses, which are the optimized results of our project. You can see these are the active power losses. You can also see the reactive power losses, which are the systems optimized systems nominal losses are 120 kVAr losses. We have placed capacitor banks of 300 kVAr rating on 3, 13, 14 bus, through which we have achieved 110 losses, which are not the optimal results. However, you can see at 10, 17, and 13 bus, we have placed 400 kVAr rating capacitor, which gives us 100 kVAr losses. However, these are also not the optimized results. However, when we place 700 kVAr rating on 17, 26, and 29 buses, we have achieved 90 kVAr losses of 120 kilowatt kVAr losses. These are our optimized reactive power losses. So moving forward, you can see the contour analysis of our IEEE 33 bus nominal system. Figure 1 shows the IEEE 33 bus nominal system. You can see you can understand the overall idea that the ascending end buses have a high voltage profile, whereas far end buses have low voltage profile. You can see these are low voltages at the far end buses. However, after placement of capacitor banks, you can see the system is optimized, and almost the far end buses are nearly equal to the ascending end buses voltages, which is our main objective of our system, of our project. You can see the overall idea of nominal voltages. You can see this graph shows the nominal voltages of the system, which are very low voltage profile. However, when we placed 600 kVAr rating capacitor on 3, 13, and 14 buses, you can see the system has improved somehow voltage. Also, we have placed 500 kVAr rating on 3, 13, and 14 bus. You can see the system has somehow optimized from the nominal losses. And the last figure, which is figure number 4, you can see we have placed capacitor bank of 800 kVAr rating on 3, 28, 32 bus. You can see the system voltages has improved from very low to the very improved voltages. So basically, you can fully understand the overall idea of the voltages, which are blue line shows the nominal voltages of the system, whereas the yellow line shows you, the orange line shows you the optimized results of the voltages. You can see the blue line is a very low voltage profile. However, the orange line shows you the very optimized results of the voltages, which gives you an overall idea of the improved system.
Assalamu alaikum. So far now, RFS discussed 33 bus system, and now I'm moving towards 69 bus system, which is more bulky and more interconnected, where chances of losses getting increased. These are the comparison of losses with and without capacitor banks. Here you can see that we have losses, nominal losses to 20 kilowatt. And after placing capacitor banks, we got 160 kilowatt losses at bus number 65, 20, and 50. The rating of capacitor 700 kVAr. Similarly, these two graphs showing the same results but different capacitor ratings. After that, we have nominal voltages of IEEE 69 bus system. Here, the first graph is showing the nominal voltages of IEEE 69 bus system. And the other three graphs are showing the improved voltages with capacitor. To compare them, well, we made one graph in one picture. Here you can see that the blue shaded line is nominal voltages. And after that, we have orange line, which is 3 capacitors, voltages at 3 capacitors. And the gray shaded line, we have 5 capacitors, voltages at these 5 capacitors. You can see that improved voltages is compared to 3 capacitors and nominal voltages. After that, we have 7 shaded line, yellow shaded line with 7 capacitors. We have more improved voltages with 7 capacitors. For now, we are moving towards PSO algorithm. So these are the graphs of algorithm, PSO algorithm. Here you can see that our system is converging at the iteration number 35th, which is 4 swarms. And after applying 5 swarms, we have our system is converging at 5th iteration, which means our system converges more fast after increasing number of swarms. These two graphs showing the same results. And these are the converging behavior of system, how system converges. Basically, you can see that these colorful dots are converging behavior. These are finding the base location where we have to place the capacitors. You can see that after converging the system, the swarms are stopped at one point, which is 28 number, which is the best location where we can place our capacitor banks to get our desired results. The other 3 graphs showing the same behavior. After that, we have PSO algorithm on IEEE 69 bus system. The behavior of the graphs are similarly like 33 bus system. Our system is converging in first graph on 33th iteration. And after applying 5 swarms, our system is converging at iteration number 14. Similarly, these two graphs showing the same behavior. After that, we have 7 capacitors, set of 7 capacitors. In these graphs, we have 4 swarms and 5 swarms like previous, but the system is more interconnected, more bulky, so our system converging little bit slow. Here you can see that our system is converging at iteration number 7th, and after applying 5 swarms, our system is converging at iteration number 8. And these two graphs are the backend converging behavior of these two above graphs. Similarly, these graphs showing the behavior, how our system converges, how our system works, what is the backend programming on these graphs. After that, we have comparison of losses with hit and trial method, and after applying PSO algorithm. You can see that we got the same results on hit and trial method and PSO algorithm, but the main difference is on the rating of capacitor. In hit and trial method, we got the results at 700 kVAr capacitor, and after applying PSO algorithm, we got the same results at 500 kVAr capacitor. So this system is 33 bus system, and this is the IEEE 69 bus system. In this, we got the results at hit and trial method. In hit and trial method, we got 160 kilowatt losses, and after applying PSO algorithm, we got 150 kilowatt losses. Also, the rating is different. In hit and trial method, we got result at 700 kVAR capacitor, and after applying PSO algorithm, we got same results or more improved results on 600 kVAR capacitor. Now, so for now, we have discussed hit and trial method and PSO algorithm. This is the genetic algorithm, which is more advanced than PSO algorithm because it has two more functions, crossover and mutation. That's why this algorithm is even more faster than PSO algorithm. So this is the graph of genetic algorithm where our system converging at 22th iteration, where the cost function value is 1.9. And this graph is the converging behavior of genetic algorithm, how our system converging and at which point it's converging point. So you can see that our system is converging at the location number 9th, where we have to place the capacitors to minimize our power losses and enhance our voltages. And these two graphs showing the similar behavior. After that, we have comparison of hit and trial and genetic algorithm of IEEE 33 and 69 system. Here you can see that we got the same results, but different in rating. In hit and trial method, we got the same result at 700 kVAR, and after applying genetic algorithm, we got the result at 500 kVAR capacitor. Also, the locations are different. In this graph, IEEE 69 bus system, we got 160 kilowatt losses in hit and trial method, and after applying genetic algorithm, we got 150 kilowatt losses. But the rating is also different. Here we got the results at 700 kVAR capacitor, and here we got the results at 600 kVAR capacitor. This is the comparison between PSO and genetic algorithm. Here you can see that we got the same results, but genetic algorithm is even more faster. It converges more faster than PSO algorithm. So we cannot rely on only one algorithm. We have to try different algorithms. So this is the conclusion of our project. In this project, we designed and analyzed the IEEE 33 and 69 bus system by using PSSE and MATLAB software. In this project, our main objective was to enhance voltage profile and mitigate power losses from IEEE 33 and 69 bus system through placing capacitor banks using PSO and G algorithm. Initially, the nominal losses of IEEE 33 bus system was 180 kilowatt. However, we reduced to 130 kilowatt losses through injecting capacitor banks. Similarly, the nominal losses of IEEE 69 bus system was 220 kilowatt. Moreover, we reduced them to 150 kilowatt losses. And these are the future recommendations of our project. This project can be useful in the minimization of power losses in large power systems. This project can be taken to the next level using IoT-based control system in which we can inject and disconnect the number of capacitors according to the system requirement. In other words, to control the excessive reactive power control due to the number of capacitors. The project can be used in all standard IEEE radial distribution network. This project can be taken into commercial use in which we can control the deficiency of voltages due to increasing loads at foreign or remote areas. These are the references where we got some knowledge and how to make project easier. Thank you.